Okay, now we'll look at problem 14-36. Okay. And this one here, you have a block sliding down an incline, and it has some initial velocity associated with it, travels a certain distance, and then it strikes a spring and compresses the spring a certain distance. Okay. Now, one of the things is that um, this spring initially already is compressed by zero point 0.5. Okay, so it has unstretched length of 2 feet, and this length defined here when the block actually strikes it is 1.5 feet. Okay, so we're given some initial quantities here. This is not a smooth surface, so it does have a zero point 0.2 friction coefficient of kinetic friction, and we have some weight associated with this block. And what we'll recognize here is that the final velocity, so it strikes this plane and compresses it down, it's going to be zero. Okay, so there's some initial conditions we also need to pay attention to. Okay, continuing on. All right, so what are we looking for? We're looking to find velocity A, so that's at the initial position at the top of the ramp. We're given some quantities. First is the spring constant, which was 50 pounds per foot. We're also given, and I define this as the unstretched length of the spring, which is 2 feet. Coefficient of kinetic friction, which is 0.2. The weight of the block equal to 4 pounds. We had a mass of plate and mass of the spring, and we made the assumption, we not made assumption, actually it was given to you that these were, the masses were negligible, so we just put that in as 0. Initial compression of the spring, 0.5 feet. The final compression of the spring, 0.75 feet. The position it's moved down the ramp before striking the plate was 3 feet. The amount that it actually compressed the spring, so that was 0.25 feet. So the total distance that it travels is 3.25 feet. Okay. All right. Okay, so the main governing equation we have is just our, work and energy equation. And, so we have some initial kinetic energy due to that initial velocity. And then we're doing work, okay, to come up with, and actually the work for the most part is against the motion of the block. So we'll find this should actually all come out to be a negative amount of work. And then it's equal to our final kinetic energy associated with our block, which was, of course, is going to be, we're going to find that to be 0, right? Because it has no velocity. All right. So I took a look at it, had some scribbles here and here. Of course, I started a little bit wrong direction. Um, Gave myself a little more room here. We have the free body diagram, and I put the forces in there. Here's this actually, I define this as F of n. So this is the normal force, to try not to confuse it with newtons. So we have a certain weight associated with the block, and of course the force of the spring, force of friction, the other direction. And then what we're going to find is we have this component along this line here of the weight that's actually going down. Okay. So we have the work of the spring, work of friction, and work of weight. I just made them all positive right here, and then I put in negative signs because of their directions. I put the negative sign in here when you actually went and calculated the works due to each of them. Okay, so the first one we're going to do is spring. So this is the work of the spring. And here's like our final compression of the spring. Here's our initial. So here's my 0.75. Here's my 0.5, right, that were defined. Okay, so the initial compression, here's my final compression. I go through, come up with a value. It's minus 7.81 foot-pounds for work of the spring. And notice, of course, the sign because it's in opposite direction of the motion. Okay, the next part, I did the work of friction. I defined it in my equation as F of n. That was the same thing in the free body diagram called NB. So here's the force of, or the normal force here. And so we could go come up with work of friction, which is just, of course, here's our overall force, right? This is the force times the distance, right? So the force, this is like the force of friction, these two put together. Okay, kinetic friction was given. So the other thing at this point, we don't know what that normal force is, but we have the displacement. So I left it in this form. And then I did the equation for what I would consider the summation of the forces in the y direction, which is just basically perpendicular to our surface, right? Okay. And the equation basically going down in the y direction, we have here's my weight, the component, the y component of the weight, where where I pivoted up and said basically the y component meaning basically perpendicular to the incline. And here's the normal force. So these are the only two things in the y direction, right? And that's going to be, of course, this is equal to 0 because there's no motion in this y direction. So you solve for that, you come up with Fn is 3.20 pounds. Substitute back into here, and I come up with minus 0.208 foot-pounds. All right. The next part is to do the work of the weight. All right. So we have the weight, and notice that this is positive in this case because it's going in the same direction as our motion. And we have, here's the 4 pounds, here's the distance, and then it's 3/5. And the reason it's 3/5, of course, is because we go back and you look at the actual free body. When you go back and look at the free body diagram, what you'll find here is the 3/5 was this part, or this part of the triangle. We use a lot of similar triangles to come up with that. Okay. So going back to for the work of the friction. So we have that 3/5. So we go and solve for that. We come up with 7.80 foot-pounds. And that's, of course, in the same direction of the motion, so this work is positive. So we come up with the summation of all the works, the different components of work, and we come up with minus 2.09 foot-pounds. Okay. Then we go and apply the original equation, the work and energy principle. So this is all the summation of all the work. I had that as a number. And here's my initial kinetic energy, which is 1/2 mass VA, the initial velocity squared. To change over from weight to mass is just, in the USCS system, is just, the weight divided by 32.2 feet per second squared. All right. Pull this over to the other side, divide by your this coefficient here, and the final result comes up to be 5.80 feet per second.